Cool. Right. So everyone must have got a notification, right?
Yes.
And we are missing one person because we had 7 on the other side.
Uh, Geeta is the one to join. I think she asked for the meeting link on WhatsApp.
All right. I shared on all the possible groups. Well, let me resume. Okay. Yes, go ahead.
Yeah. So hi everyone. So today is going to be our first invited talk as part of Dhyuti seminar series of talks, where we want to convert this into a platform for those chasing hard problems in science and tech, focusing currently on climate frontiers. And today's invited speaker is Dr. Satish Kumar, who is also our inaugural speaker for the series. Uh, Dr. Satish Kumar is the CEO of EyeClimate Inc. and a Schmidt Science Fellow at Stanford University with over 12 years of research experience, including 7 years focused on the intersection of climate science and artificial intelligence. He holds a PhD in computer vision and has spearheaded cutting edge projects with prestigious institutions such as NASA JPL, the Smithsonian Institute, the Aerospace Corporation, and the Harvard University. His work spans diverse areas, including greenhouse gas emissions detection and wildlife tracking in the Masai Mara and Serengeti. Satish has published extensively in premier conferences like CVPR, NeurIPS, BMVC, and WACV, and has delivered talks on AI for climate change and wildlife at these conferences as well as the Mara Elephant Project as well as the Mara Elephant Project in Kenya. His contributions to GHG detection and wildlife monitoring have received special recognitions at CVPR. In addition to his academic achievements, Satish brings 5 years of hands-on experience in OS development from his tenure at Samsung R&D in South Korea and India. As the CEO of EyeClimate, he leads the development of AI algorithms for hyperspectral and multispectral imagery, as well as aerial imagery. His expertise in modeling multimodal data, integrating satellite images, weather reports, and other ancillary information enables the creation of robust AI algorithms for anomaly detection in extremely high dimensional data. At iClimate, Satish oversees the core research initiatives to deliver state of the art solutions. Over to you, Dr. Satish.
All right. Thank you so much. It sounds weird listening to your own thing, like what that I sent to you. But okay. All right. Okay. Cool. Thank you so much, Rahul. And I don't think we need to like spend more time on the introduction, but I'll just make it like quick. So currently I'm a postdoc at Stanford and going along the same lines, extending the work of what we started at UCSB and at iClimate and further in like extending it not only towards detection. Now we have taken one step forward. We have gone towards mitigation too, where we are working with a group of particle physicists, electrochemists, and me as a signal processing person. And that's where we are going forward. So I'll show a glimpse of that also towards the end of the talk, like what we have been able to achieve in last 9 months. All right, so I'll share my screen. And please let me know when you can see it.
Yep.
All right, cool. Thank you. So, iClimate is the name of our company, and Methane Mapper is our flagship product. And today I'll go in detail about Methane Mapper only. And also, I'll walk you through the process, how we came to it. And also, towards the end, I'll show you some test example, the pilots we did for different type of oil and gas operator, different kind of locations, and that all. So the problem we all are aware of, we are dealing with the problem of undetected methane emission. And why specifically we want to focus on methane emission is this one single gas is responsible for 30% of the global warming. And to put into perspective, the amount of heat that carbon dioxide can trap in 100 years, like methane can do that in 1.2 years only. So now imagine like how quickly or at how an accelerated or exponential rate we are heating up our planet. The good part is, so the good part is like almost 11% of it comes from oil and gas resources, and those are point resources. So like point sources. So we know where the emissions are coming from. And that gives us a motivation that if we can find out those and address those, then at least like 10 to 15% of the problem is solved. So it's a low hanging fruit. And other sources are like we have emissions from landfill sites. Those also could be improved a lot. We have emissions from agricultural sites. We have emissions from dairy farms. Surprisingly enough, one single cow produces 250 liters of methane per day. So that's a lot of methane that comes out from one single cow. And people have farms which have like 10,000 cows. So those are huge. So so these are other sources where we can improve the emissions and control and like have a dent on the global warming, a little bit of dent on the positive side, I would say. So the oil and gas industry, so that's what we will be focusing on today. The reason they have not been able to address this problem well is the current process is extremely labor intensive. And by that I mean is like they have since methane is a byproduct, so they most of the time either it comes in pocket, so they just releases it, and other is like there are pipelines, gas pipelines, which ships the gas from one location to another, and those are like thousands of miles long. And over there, literally they drive vehicles next to the pipeline for thousands of miles in middle of nowhere to address this. Recently, there have been some improvement on this, where people do aerial surveys or do drone surveys or helicopter based or like satellite based monitoring too. That have improved the process a bit, but now the another bottleneck is so there is a baseline detection. And then once they go to finally actually figuring out which one is a methane plume and which one is not, because there are a lot of false positives, there are a lot of things on the ground which mimic methane presence. So they have to manually go through every single one of them. Okay, that this is methane plume, this is not a methane plume, this is methane plume, this is not a methane plume. So even on the technical side, when we have made efficient, the process has become very labor intensive. So now imagine if you have to map the whole planet. Like you cannot employ that many people. And it's a safety issue for operators and people living in the vicinity. Uh, okay, so like people living in the vicinity, and that is an example I will give you is it's an explosive gas and it's extremely dangerous. And we have seen cases of when the like a gas cylinder burst. Recently, I think a couple years ago, there was a leakage from a gas pipe in gas pipeline in South Korea. Temperature were extremely low, so the gas did not rise up and it spread out like fog up to like knee level. And then there was a people thought it was fog, and there were people roaming around and walking around. And then there was a tiny spark in the nearby transformer, and within seconds, the whole street blew up. So that's how big of a safety issue it is. So not only like a financial loss on losing the gas, but it's big on the safety side. Yeah. So to solve this problem, we came together as a group of PhDs from UC Santa Barbara and Stanford, where we have expertise in computer vision, remote sensing, image processing, and photonics. Because we are looking at this problem from the perspective of image processing. And I'll tell you more as we move forward. So, Methane Mapper. It detects and measures methane leakages from oil and gas infrastructure. That's our like first focus. And for this, we use both airborne sensors and satellite-based sensors. And our method is fully automated. How it helps over here is like, as I mentioned in the previous exam, like a previous slide, people do ground level monitoring, and even if they're in the automated process, they do manual like a selection of that this is methane and this is not in methane. So we have been able to reduce that human in the loop by like a high extent, and now we have automated that process. So basically, you throw more compute at it, we can map the whole planet. So that's how efficient we are at it. And we provide complete monitoring from global all the way down to local. And by that I mean is we can monitor a whole state, and we have solutions where we can monitor continuously on a local site a leakage as low as like 100 grams. And we deliver all this with more than 90% accuracy. And these are the few of the benchmarks of our technology. From satellite imagery, we don't own a satellite yet, though we target to launch two CubeSat by 2026, quarter 2 or quarter 3. We'll see how we land over there. So from open source and commercial, we can detect as low as like 100 kg per hour emission. And from aerial based surveys, where it's like when we're doing collaboration with JPL, so they have a hyperspectral sensor as a $500,000 sensor. From a height of 4 kilometers from an hyperspectral image, we can detect as low as like 10 kg. And from on-site sensor, where we are putting the laser sensors on the site and they are doing continuous monitoring, we can detect as low as like 100 grams per hour. So that's how. So basically, we can tell you if there's a leakage from a tiny rivet or a bolt on a tank, we can precisely pinpoint that, okay, yeah, there is a methane emission from there. So, and to make this technology accessible to everyone, we have made the workflow very simple. Like we take collect data from operators or from different type of sensors. So we have made it agnostic to the type of sensor, agnostic to the data modality also, and agnostic to the resolution also. And we pre-process it in real time, and we analyze it, and then we provide exactly like actionable information. That's precisely where methane is coming out from, how much it is, and where all the gas plume is spread out. So this is not like a gimmick picture. This is an actual detection we did in Los Angeles from a tank that was leaking, and it was approximately 7 kg per hour emission. So so if there are questions, you can stop me in between, or if you want, like we can have like 10 minutes towards the end also for discussion. So now I'm gonna change gears a bit, and I'm gonna go a little in depth towards how our technology works. So this is a snippet from our first paper where it shows the architecture diagram of how we built Methane Mapper. Our current method is like exceptionally accurate, and I mentioned it's highly scalable. We are very robust against false positive, and I can say we were the first one to figure out this problem from the perspective of image processing. So this is how like a methane mapper works. JPL does aerial surveys with a hyperspectral sensor, and that was initially like how they did it for us. And the left hand side image that you see over here is an hyperspectral data cube. And by hyperspectral, I mean is those whatever we are seeing on our computer screen right now, those are 3 channel like RGB. Now imagine like instead of RGB 3 channel, which is in the visible domain, 400 nanometer to 760 nanometer, we extend it the range to 2400 nanometer, that is shortwave infrared, and we cover image at every 5 nanometer step size. So it creates a whole like a deck of or 3D cube of the images. And that's where the Z dimension is. We have 432 channels from 400 nanometer to 2500 nanometer. And as the plane move forward, so we have a grid of sensors which keeps on collecting the image in a push broom manner, and then you get your whole image. So each survey is approximately around 30 kilometers long, and there are around 512 sensors, an array of sensors. So the width is approximately 1.5 kilometer wide. And the goal is we process it. And as you can see the red mask on this side, we want to identify precisely where exactly the gas plume is spread out and how much is the concentration. We also want to find out what is the rate, emission rate, whether it's 10 kg per hour, 100 kg per hour, 1000 kg per hour. And we also find out the precise location where exactly it is coming out from so that someone can actually go and address this. So this is a very classic example of what all information is hidden if we look beyond RGB. So as I mentioned, like on our computer screen, we saw this, and the motivation, like why we need up to shortwave infrared to see methane emission. So this image was published in New York Times a couple of years ago. This is not an image, actually, this is a GIF. But everything seems super benign. And if you look slightly beyond the visible spectrum, you'll find a large amount of emission happening from that chimney. So this is where why we want to look beyond the visible spectrum to find out if there are gases or not, if there are some kind of emissions or not, because it's an invisible orderless gas. We cannot see things in the first frame, like in the visible range. So to tackle this, we developed a series of work. Our first one was in 2019. We built an ensemble-based approach that was based on mask RCNN, and the output was same. We were generating segmentation mask, but we were not precisely detecting concentration that time. And then in 2023, we updated our method, and we instead of ensemble, now we have a single pipeline that the image I showed before, and which is a transformer-based, extremely efficient and accurate architecture. We brought in chemistry and the chemical and physical properties of the gas too when we were designing the network, so that we are not just going on designing a black box, but we are informed by the chemistry and physics of the gas. And that is our spectral linear filter. So, and to start this problem, of course, like you need a large amount of ground truth data, and that was also missing in this side. And I think that might be one of the problem, actually, why could have been one of the problem why this people didn't look on this side from image processing perspective, or if designing like a computer vision algorithm. So to address that problem, so we curated the largest hyperspectral data with proper ground truth and concentration maps. We call it methane hotspot data. You can check it out. I'll share the link. It's publicly available. And we got in touch with a couple of nonprofits and California Air Resource Board and few other sources when we were curating this data, because we needed those ground truths. And we also needed someone to verify those ground truths. And how those were done, verification was done is the nonprofits, they did their manual verification. And then we requested California Air Resource Board to actually visit those locations, like few of those locations, to verify if whatever we were seeing from the aerial imagery is actually there something or not. So that why we have both like expert verification on the processed image too, and we have the physical ground verification too. And also, and we separated out the whole data set in 2 points, like two parts: point source and diffuse source. Point source is something where the emission is coming from a single point. Basically, if there is a leakage from a pipeline or leakage from a fume hood type scenario, or leakage from a chimney, so those are called as point sources. So you have no precisely high concentration at one point. And second one is a diffuse source. These are emission from agriculture site. For example, dairy farms. Though each cow produces 250 liters, but they are spread out over kilometers and the fumes are very thin. So those are diffuse sources. Another example is degradation of biological material around what are they called, power, like water dams. So that also is one source of emission. Why rice cultivation is another large source of emission. So we have one project going over here at Stanford. We are looking at emissions from the rice field, and we can detect as low as like 2 parts per billion. So the sensor is so sensitive that we can, so it's a lab built. So sensor is so sensitive, we can even see here, like it beeping inside the lab environment too, because it picks up methane molecule in the lab too. So basically someone farting, we find it out. And these are the statistics of our data just for comparison. So the only previous data set that exists before this was one collected by JPL, and that have only 161 methane plume site, only 46 pipe like flight lines, and we curated approximately 4,000 plume sites, covered 8 years of range, not just 1 year, and different regions. Previously, it was just in the Four Corner region in New Mexico, Arizona, California, and one more. And we covered like from dry region of Texas to semi-arid region of California to extremely wet region of Virginia, because geography actually plays a big role on what you can see and what you cannot see. And we provide both the concentration maps of a lake gas and also the bounding box. So we provide like a very diverse data set now. And I think till now there have been approximately more than 300 downloads within a year for within 1.5 year of for this data set. So coming back to like a methane mapper. So now we know what is the problem we are solving. We know the bigger picture of like how we plan to solve it. And we know that, okay, what kind of data are we going to use it? So let's jump in. So the first part of is the spectral linear filter, where we actually want to bring in or model the chemical and physical properties of the gas into our when we are designing our network. And why it is critical is, so methane have absorption around 1600 nanometer and around 2000 nanometer. The reason for those is because this is a like CH4 molecule. We have carbon in the center and we have four H atoms around in the side, and it's constantly spinning at around certain x's. So when a light photon hits the CNH bond, so it gets absorbed by that bond. And based on at what axis we are looking at, so basically which harmonics we are looking at of the spin, so we can see like how much of the light photon is going to absorb. So 1600 nanometer is actually a third harmonic. So we have actually much weaker absorption. 2000 nanometer and onto 2000 2400 nanometer is second harmonic. We have slightly stronger like absorption. And beyond 3000 is like precisely when it hits like right on the CNH bond. And that's where we have the strongest absorption. But it's very hard to design sensors beyond that when you're looking from such a far distance. So the focus is only, we have enough information from 400 to 2400 nanometer that we can actually detect methane. So we modeled those inside our spectral linear filter. And how we did that is, so basically we modeled it as additive perturbation. And over here, by that I mean is, let's say you are looking at a pixel on the image, the data cube that I showed you from the top, at the ith pixel, oh, where is my, ith pixel, over there, that is a combination of some variable called as t and r some variable called as ri. Ri is basically whatever the solar radiations which are coming directly from the sun get reflected from the ground and again get collected by the sensor on this side. So it have a two pass through the atmosphere. That is like like I mean a standard scenario when there is no methane gas. Now imagine in the path there is methane gas too. So there will be additional absorption, and that is the t variable. And this is basically the absorption spectrum of methane. If there is methane, so it we can see it over there. So this is how it is modeled as an additive perturbation. If there's no methane, we'll see the standard solar like radiation absorption only by the ground and by other gases and then received by the sensor. And I was showing, so this is where around 1600 nanometer, the T signature, methane have some absorption, and around 2400 nanometer methane have strong absorption. That is our T signature. So to do this, we first work on something which is called as Lamach filter. This is not new. This has been in information theory for over 3 decades now. And it's basically used for removing noise from a signal and enhance the very weak signal, like basically improve the SNR. And how that is done is over here, I'll skip over the like too many technical details. So this XI is the pixel we are actually looking at, this one. And this is we just getting rid of the mean value. Now to model the ground, because the ground is very dominant and the gas's plume is or gas pixels are very weak. So we look at the absorption, where T is the signature that I showed you before, and R is the covariance of the background distribution. Basically, like I mean, we how we do that is we take every two adjacent pixels and compute a covariance matrix of every single one of them on the ground and then average it out. So that's what we capture the covariance of the background, and how it works. It enhances the visibility of T and suppresses the dominance of the background. So that's how you can explain it in from 10,000 feet. And the output H that we get over here is basically our H we get is basically our enhancement we get given there is a background covariance R, and given we are looking for a known signature T, how much it exists in the given pixel xi. So we are operating pixel by pixel right now, only like that is like column vector. We take the whole column of 432 and we are operating pixel by pixel over here. Till now, we haven't exploited any spatial correlation. We have only looked into the spectral correlations. Okay, so this is our match filter. So this generates our initial crude information about methane. Now coming to the second part. Over here, so this is where our spectral linear filter fits into our area, into our architecture. So what it does is this single image is very big. So it's approximately 100 gigabytes to 150 gigabytes. So we do initial processing on the channels, and the quality of match filter is it will precisely tell you where all there's a potential methane source could be, though it's dominated by approximately 60 to 70% false positives, because there are thousand other things on the ground which mimic methane presence. They could be like concrete structures, hydrocarbon paints on top of roofs or warehouses, roads, they all mimic methane presence. So basically, even if there is a weak gas over there, like it will be dominated by everything of those. But match filter picks up everything, whether false positive, true positives, picks up all of those. So we know even in a big flight path, where exactly do we want to look, if that is a methane or not a methane. So that part is done by match filter. And now the next part is how we designed our architecture is. So we built as a two pipeline on top of each other. We process the RGB information separately. Now we have started exploiting the spatial correlation. Till now, we only looked at the spectral correlation. In the spatial correlation part, we looked at RGB images, like how exactly the ground distribution is. And also we looked specifically, we filter out where methane has strong absorption from 2000 to 2500 nanometer. We take those, we extract the features out of it. So the backbones are basically simple ResNet 50 architectures, nothing fancy. And then we pass that information through our transformer encoder. And this transformer encoder is basically a couple of attention layers, I think around eight attention layers that we have in the encoder. So the reason I kept it small is there was no innovation. We used an off-the-shelf encoder over here. It was inspired by detection transformer from Facebook. Now the novelty comes in the part, given we have the encoded feature of where there might be methane and how the ground looks like. Now, how do we differentiate that which one is a false positive and which one is precisely methane? We could have done it without this spectral linear filter too, or spectral feature generator too. We could have done it without bringing in the chemical and physical properties of the gas, but then that would have needed at least like 10,000 samples, because then we would have forced the network to even learn the representation of a match filter too. So we provide that prior information. So that means when we have the encoded feature from the raw image, inside attention layer, there are three core variables. How they are modeled is we have key, values, and queries. Queries are basically what you question your keys and it returns a corresponding value. Example is, let's say you're translating a sentence from Hindi to English to Hindi. Then your keys are all English word and your values are the corresponding Hindi words. And the query is you check like my name is Satish, so you'll query my and you'll check in the keys where it matches. So that's like it compute an attention over there between like a query and the key, and then it'll return a corresponding value. So that's how it works. Okay, that like my and it's like mera, it will return that. In standard training paradigm, all three of them are randomly initialized. Like they are completely random vectors. That means you have to throw in insane amount of data. So transformers are infamous for using extreme or large amount of data. So you have to throw an insane amount of data so that it learns what a query might look should look like. It learns what a key looks should look like, and it learns what a value should look like. And that is just based on an end ground truth that is provided to you, and that might be completely different modality on what these three vectors are seeing. So that's why it becomes a difficult problem to optimize this. What we did in our case is we provide a prior information in this query. So, and that is that's what comes from our spectral linear filter. We provide a prior information, so we already told that these are the potential locations where you might find methane. So in this query definer, so we generate a random query vector and we do a cross attention with what is the output of our match filter. So that way we have kept a randomness too, that okay, if there is something that we might have missed, and we ensure that it's learnable too, that it keeps on evolving over time. But it goes and queries that into our encoded feature vector from the raw image. And that's where, since we provide this as a prior information, it already knows where in the image, and that is the encoded feature vector of the raw image, it has to go and look and query for whether that is methane or not. So that brings down our, no, actually, like brings down our training data size from requiring 10,000 samples per class to approximately 3,000 samples. And that's where we had a huge boost in efficiency of training the transformer because we provide pre-informed queries. So, and then the decoder is like we provide our refined queries, and when we have encoded raw feature vector, and then it generates a refined value that contains precisely that, okay, this is methane and that is not a methane. So it like eliminates the false positive. So I'm talking about the forward pass in the like when it's already trained. And then these are just like deconvolution layers for predicting a mask, and like two linear layers for predicting the bounding box. And we train it on the given because we know the corresponding ground truth too. So that's how our decoders get trained. And that is how our end-to-end architecture works. So like how we encode the, reiterate, how we encode the prior information, and that prior information is the properties of the gas. And then how do we make the transformer training efficient to capture those correlations and differentiate from the false positives. And now I'll show you some examples. So this is one of my favorite example because this is a very challenging scenario. And this we did a benchmark test with one of our customers actually, and they were running on whatever method they have. So their detection time was approximately 40 to 45 minutes, and accuracy was around 60 to 70%. And that given they were like, after doing the initial processing, they were manually pinpointing that, okay, this is methane and this is not a methane. So the first image is actually ground terrain visualization, RGB. So there are a couple of sites and there are strong winds too. And this is methane mapper output, where we were able to differentiate between plumes which were next to each other pretty close, and even under different wind directions too. I mean, same wind direction across the whole. There's like a weak plume over here, like 30 kg per hour, and this is the largest one, 250 kg per hour. And this is just an overlay of the same image on top of this. So this is an example test that we conducted benchmarking with the current customers. And they did it in 40 minutes and we did it in 3 minutes. And and our accuracy was, I think, about 90%, 93% in this case. So that's how efficient and like both in time and how good in accuracy Methane Mapper is. Then we did another pilot with Marathon Petroleum. So where they were interested in using OGI's camera output, and OGI camera are the ones which operate beyond 3000 nanometer. So literally you can actually see the thermal signature. And this is, I consider, as an easy scenario because there is a good contrast in the compared to the background and what is there in the foreground. And we tuned our model, and now we were processing almost real time, where we can not only track the plume live, but we can also tell you per pixel the ppm values over there and how it changes as you move away. So, and there's another oh, I did not kept it, like I removed it, huh? So there's another example to have where like I showed, like even in a challenging scenario where it's not as easy as a clean background, like an open sky and stark temperature difference. We also have like from a leakage from a tank, and there are a couple of other messy settings. There's another tank, there's pipes and everything, and they're different temperatures. And we're able to track a tiny leakage from that tank also. So now, so these were our pilots. So currently, we are processing the data from ExxonMobil across the whole Texas Permian Basin. And ExxonMobil is one of the biggest oil and gas producers in United States. So Methane Mapper is being used to process all of their data. So this is the company we are currently partnering with Scepter Air. So they have their own sensors, and we are the data processing company. We are also working with a company in UK, Perja Metallia, because the methane regulations have gone away in US for obvious reasons. So we are monitoring approximately 100,000 kilometers of gas pipeline in France and Netherlands, where these are basically roof mounted sensors. These are laser sensors. They mount them in the roof of the vehicle and they drive it around next to the pipeline, or they put it on under a helicopter and they drive it flight around. So we are processing the like approximately 100,000 kilometers pipeline over there. And there's a slightly mismanagement over here of the text. So there's another company named SpectraView, which is a UCLA-based startup, and they built an extremely low-cost hyperspectral sensor. The one that I showed you before, the data cube, that is from JPL, that is a $500,000 sensor. And this sensor that we built, that SpectraView built, is $20. Extremely cheap, really good, and still under construction. And our target is we plan to launch two CubeSats in low Earth orbit by second or third quarter of 2026 for test. And we want to start with methane and then go for other use cases. So now, like given all this, so let's talk some money. So the total global market of methane is approximately 14 billion, and that I'm only talking just the detection. I'm not even talking about mitigation for like people are doing. So mitigation, just to give you like a ballpark number, like if there is an abandoned well and someone has to do like a abandoned well and it is leaking methane, and if it's on the site, like sorry, on the land, then the cost is approximately $500,000 to close it and seal it. And if there is same well which is leaking methane is offshore, like near ocean or something, there it costs like $2 million to seal one single one of them. Alone in US, there are approximately, I think, 1.9 million such wells which are unknown. Nobody even knows. And that's a huge market. But now, like current administration doesn't need to remove that. So this I'm talking about detection. The market we are focusing on is oil and gas infrastructure in US, Europe, and Australia. And we are starting with oil and gas pipelines specifically near residential areas. And why we are focusing over there is because that's where the rules and regulations are very strict, because it's not only the leakages and not only the global warming, it's the safety of the people. And I told you the South Korea example. And the one of the pilot we did in Los Angeles with one of the oil and gas operator over there, the owner told us that California Resource Board do random checks, and if someone is defaulted couple of times, their licenses are cancelled. So it's not only global warming, not only like leakage, money loss, but they can lose their whole business too. So yeah. So that is where we actually ended at, and we are still expanding in different directions. And now we started with methane, and that is our goal to build like a traction market. And now we are expanding towards building a foundational approach where we can not only detect methane gas, but the goal is you give me any latitude and longitude on the planet, and I'll tell you the composition of whole atmosphere around you, both in the atmosphere and on the ground. So basically, I'll tell you all the gases that are around you. I'll tell you all the pollutant around you, and on the ground I can tell you for example, landscape changes that has happened, fire risk that is there, flood risk that might be there, how the precipitation changes, and what can you expect in future. So this is a proposal we submitted to Indian government, and then I think a couple of people are here on the call. We all worked on it and submitted together. So this is what we are focusing towards in the future. And parallelly, as I mentioned, we have been working on mitigation too. And people who are from northern India and who know, then everyone, like all of those might be aware of the situation in Delhi. The AQI goes up to 1,000 or beyond 1,000. The situation is very bad. And that's where my work at Stanford started, where we built a mitigation approach where we are not altering the atmosphere, we are not using any chemicals, we are not altering the people's behavior on the ground, that okay, odd even rule or controlling the vehicles or anything. We exploited the properties of the pollutant itself so that they can precipitate and fall down on the ground. And I'll show you an example over here. So this is like a pollution chamber we built. And the moment we start the chain reaction, so see, it clears. Oh shit, where is my cursor? Okay, huh. See, this is within 5 minutes, it clears up. So our goal is to next turn this into like a scalable setup where because our like we started with not like where we can suck in the atmosphere, because that is completely impractical solution. You cannot clean the atmosphere that way. You have to start a chain reaction that can just spread in the whole atmosphere on the whole, where like people sleep with a smoky sky and they wake up to a blue sky. So within 8 to 10 hours, the whole thing just precipitate down on the ground. So our goal is to like test the scale of it, so that how we tackle it. And then when the problem hits in Delhi this November, we would like try to conduct an experiment in cricket stadium in Delhi, the Firoz Shah Kotla Maidan. And we will try to see if we can, inside the stadium and outside the stadium, if we can generate a stark difference in the AQI. So yeah, that's all. And to stay in touch, you can follow us on, I think this is LinkedIn page. Yeah, might be LinkedIn page. Yeah. And that's all. Thanks.
I would say amazing presentation. Thanks, Satish. I think you talked a lot about methane detection, and then a lot more on the technical aspects of it, which is quite dense. And I mean, it was very appreciable. And I think it's proper deep tech, right? This is what proper deep tech is. You have an end goal in mind, and then you backtrack and build a solution for it, which can go as technically dense as possible. And this shows it. And I'm really excited about what you presented about mitigation and what you could do on a global level. And also very excited about the experiment that you'll be conducting in Delhi. I would be eager to know about how the experiments turn out, and looking forward to that. And if others have any questions, we could take a few of them now.
Yeah. Oh yeah, we can take a few questions. We started 20 minutes late, so
Yep.
I think it might be too late for people in India for questions. So
Yep. So if
Hi.
you want, yeah,
Hello.
Mira,
Hi.
go on. Yeah.
Yeah. Hi. Sorry. So, I mean, I found the presentation really interesting. Um, so I guess my question is because I'm not very familiar with the sort of methane landscape currently in India. What are this and because my background is more coming from a financial perspective. So I guess when you're trying to scale these, etc., what are the sort of largest challenges that you face? Um, yeah, because I'm curious to hear from your experience in this particular area. Yeah.
okay, I can comment on the methane side because on the mitigation side we are still yet to tackle that.
Yeah.
So so the largest challenge is never the challenge that you accept, like that you expect actually. So whatever is in mind, like theoretically, oh, that is going to be a bigger problem. That is never the problem. So for example, for us, when we built the continuous monitoring solution, and we were like, oh yeah, we'll partner with someone, we'll like buy the sensors and we'll deploy them some like on all the oil and gas site and do continuous monitoring and make like $100 million per year. But we later realized hardware is a very, very, very messy business. Like the amount of approvals that you have to get and like make sure like some people deliver things on time. Make sure there are people who are like able to take responsibilities because you are installing something at an extremely sensitive location. And then like how you also ensure like the security and privacy of the data, what you're releasing, what you can't release. So all these are much bigger challenge, and it took us 8 months to figure those out. Though the difficult part was building the solutions that we did in like in a quicker time span.
Okay.
So these are the kind of challenges I would say are much bigger problem.
Okay. Yeah. Thank you.
There's just one comment for Mira's question I would like to add is that so I think the government of India is also very well aware of methane as a big problem and problem with emissions. So just a few months back, the Department of Science and Technology (DST) had a very ambitious called proposed call for proposals called M3T, uh, methane detection and I think mitigation or something like that. And it was mostly aimed towards universities, but the call itself was very well. They did a very well market on like where the problems are, and like where all methane was being a main source of pollutions. Classified them into like different categories and had laid out the call for proposals. So that is only one small example, but I think like that had a lot of information on this perspective, like on methane in India, methane pollution and mitigation in India.
Yeah, and yeah, since Lakshman brought that up, so me and Lakshman, we actually like wrote a proposal with IIT Delhi on that call as like co-PIs. So we'll hope, let's say, like I mean, what if we get it or not? But yeah, so like in India also they are actively looking into and then actively putting in money to like address this problem, because though we are not an oil and gas producer, but we are a big consumer also, and landfill sites is a big problem around the country, because waste management is a big issue in our country. We do not manage it well. So most of them like are mismanaged, and there's a lot of degradation and that of both biological and other materials, and there's emissions everywhere. And then example is nearest to Delhi, that is a huge problem. So it's not a landfill site anymore. It's like like an Himalaya of waste. Oh, Rahul, we can't hear you. Nope. No, still can't hear you. No audio. Maybe you switch from your headphones back to your computer, maybe? Uh, It's good we lost it towards the end of the meeting.
Or maybe Rahul can also put your message question in chat.
Mm. You can type in chat, it's okay.